Thanks. Well, let me start by thanking the organizers for bringing us all together here. It's been a fantastic event, and also for giving me the opportunity to present this semi-classical work to you all. So now this is work I've been doing with two individuals who are unfortunately not in the audience today. They're postdocs, Rafa in Edinburgh and Matteo based in Paris. Since they couldn't make the meeting, I thought I'd shove their pictures up there because, you know, these are good guys and it's good for you to know who they are. Okay, so let me start with a little bit of motivation. Well, I think we all know, those of us sitting in this room, standing I suppose, that the program of using amplitudes to do gravitational waves has been a great success. We've heard a lot about it in this meeting, but in particular Radu gave an amazingly comprehensive summary earlier this morning. But of course it raises a question. The scattering amplitudes are inherently quantum mechanical objects. So when we use these scattering amplitudes to talk about gravitational wave physics, we're leaving stuff out. We leave out some diagrams, we throw away some bits that we don't really want. And we can ask ourselves, what if we kept those bits? And we use our methods to address interesting questions in semi-classical physics. Of course, there are a lot of very interesting semi-classical phenomena. What I want to tell you today is that the answer to this question is yes, and that Hawking radiation is an example. This is something that is amazingly close to the techniques and technology we've been developing over the last couple of years. So this talk is going to be nothing but a translation of Hawking's original paper into the language of scattering amplitudes. It's just a pure translation. There's nothing new. But still, there are some interesting points along the way. I'm going to start by giving an overview of a certain scattering process, which is sort of intrinsic to Hawking's work. So this is a genuine scattering process. One particle comes in, one particle goes out. It's scattering off some blob there. And then I will just cross to get the pair production. So just take one of those legs, in state, and you just cross it into the out state, and now you're good to go in pair production. Now throughout, I'm going to work in a situation where my particles are scattering off a particular background metric. So the metric goes by the name of the Vaidya metric. That's the expression for it there on the screen. It's a Kerr-Schild metric. So the K there is our usual friend, which we see in the Schwarzschild solution, for example. In Kerr-Schild form, it's just K.dx is dt plus dr. Now this metric would be particularly familiar if that theta function was just 1. Just be the Schwarzschild metric. And then we would all know that scattering a particle of this is, related to the dynamical scattering process in some way. This would be the 0 SF term, in our nomenclature. So, working in a background is not so unfamiliar to us. This background is a little bit more unfamiliar because it's time dependent. Obviously, there's this theta function in there that makes things a bit different. Now, the fact that this theta function is there is telling you that there's no black hole somehow in the far past, but there is one in the future. And correspondingly, some radiation, some matter falls in, collapses in, and it forms the black hole at the origin here, and at time 0. So here's a picture, some sort of cartoon picture of this space-time. So in the far past, there's just some flat region. This is before the radiation gets in. I cunningly drew the radiation as this red line here, so that's just some bunch of massless particles basically falling in. And in the future of that region, there is a Schwarzschild zone. So up here, it's just ordinary Schwarzschild. The theta function is 1 now, and there's a black hole sitting around here. It's worth noticing that. So the blue line here is the event horizon, and it's maybe worth noticing that the event horizon, event horizon forms in a sense before the radiation gets there. And that's because if you're an observer just sitting around in this little part, well, you might think that everything's great, but when the radiation goes by, well, you didn't have time to get out, so you're stuck. Okay, now the scattering process just involves taking a particle and scattering it right through this geometry. We choose a spherically symmetric particle. Various reasons for that, but one particular reason is that since the whole situation is spherically symmetric, this this takes advantage of the symmetry of the problem. So I'm just going to take some spherically symmetric particle and scatter it right through the origin. Right? Now I want it to come out. It's a scattering problem. So something comes in, something comes out. So we need to think a little bit more about the picture here. The radiation, as I said, is that's collapsing in to form the black hole. Is this red line? That's associated with some parameter here in this line. So this line is the t plus r axis, and the radiation is on the line t plus r equals 0. The event horizon itself comes back out into that t plus r at some earlier time. It's a short little calculation to show that the earlier time is minus 4 gm. It's sort of obvious it's going to be gm, right? It's event horizon. It just happens to be a factor. So I better shoot my particle in before that. So at some advanced time, t plus r equals p. Shoot it in here. It's moving in flat space. It goes straight through the origin, and then as the radiation goes by, it starts getting dragged, redshifted, so forth. So that's the scattering process you want to describe, right? It's going to be some kind of amplitude describing this scattering process. And essentially what I want to do is to compute the amplitude, this scattering. Useful to note, I'll make various comments about this later on, but there's some perturbative parameter in the problem here. So the perturbative parameter is this distance, this v, over the 4G, essentially this distance, so where the event horizon basically goes back out. So this is something that you can go ahead and expand in, and the expansion in that is analogous to the PM expansion in classical applications of scattering energies. Okay, so I'm just going to use usual methods that we developed to understand this scattering process. So I'll switch on initial state, psi, so this will be the state for my particle in the far past. I'll write it here as some integral over phase space. This d phi of p is my patented notation for the integral over the phase space of a non-shell particle. I'm going to pick a massless particle. It simplifies the problem, and it's also they're the most important ones for the actual radiation. Now, I've written the phi here, so this is the wave packet of the particle in the far past. I've written it in this equation in a slightly different way, basically just as a Fourier transform. It's a one-dimensional Fourier transform with respect to this v, so v is going to be the advanced time. And one-dimensional in particular because I'm assuming that the phi here really only depends on the energy, so it doesn't depend on the direction of the momentum. Now that's because I wanted a spherical state, right? So I'm integrating over all of the different angles there. So, so this is just some way of writing a spherical state. It's an L equals 0, M equals 0 state, which is written in a particularly convenient form. I like my plane wave states. This is just one way of cooking it. Okay, now we can again rewrite this just in a form that we're familiar with. So I've written this exponential here as e to the I p dot b. That's a form that I see when we're using, considering scattering of Schwarzschild. So the b here is something like an impact parameter, and the only novelty really is that the impact parameter is time-like rather than space-like. Normally we have some space-like separation from a black hole, but here the thing just goes straight through the origin some time before the black hole forms. That's the main novelty really, is that you get through the origin. Okay, well now if we were to study, a quantum particle, you get its wave function in all its gory detail, that would be a hard problem. It involves solving the Klein-Gordon equation in a time-dependent bracket. It's hard enough in Schwarzschild, it would be harder here with Vaidya. But there is a situation where the physics simplifies, and that's the case where we take the energy of the particle to be large, the energy of the particle I'm throwing in, make that energy large. This is the geometric optics regime. So in this regime, I can write the wave packet of the particle. Its phase is something like this. So there'll be some s, phase s. I'm pulling out a parameter eta here. And the idea here is I'm going to think of that eta as being analogous to h bar. I'll think of eta as being small, making the energy large, and then I'm just going to calculate as though this eta is a h bar. Now here I make contact with Julia's talk. There'll be more points in contact with Julia's talk later. Julia mentioned this geometric optics regime lower left of this diagram in her talk. Yeah, very simple. Okay, so in this regime, well, I mean, if we were doing ordinary classical applications of scattering amplitudes, it would all be extremely obvious. There's some tree-level bit, would have a 1 over h bar. There'd be a one-loop bit. It would have a 1 over h bar squared. These are these iteration terms. A two-loop bit would have an extra. And all these things are going to exponentiate. We know they will because we're working in the geometric optics regime. Here, the blob is this Vaidya background, but still, that's not so different from really having some kind of particle there. So this really is something tree. This is, got the structure of a one-loop thing. You get loop integrals out of this, etc. So we just have to go ahead and compute these things and add them. Now the tree calculation is pretty straightforward. I'm just scattering this particle off a background. Here's the interaction action. The h mu nu is this inertial h. Go ahead and calculate. There's some little bits of tricks to get a nice answer out of it, but you work a little bit, out pops this log. And it's a very familiar sort of, the structure of this is very familiar from our usual story. So yeah, even the factor of 4 is very familiar. Now, adding up the diagrams, well, they exponentiate because we're in the geometric optics regime, and this is the form that the final amplitude at the sum of all these diagrams takes. So it has this exponential of this log. All right. So at this point, it's useful to pick a particular kind of incoming state. And the simplest thing to do is to say, well, I'll actually just throw in a plane wave state. So here's a spherical plane wave. So it has an initial energy E0. I'm integrating over the angles to get the spherical state. And I'm being a bit, maybe a little bit evil here because, I told you earlier that there's a perturbative parameter. The perturbative parameter is some sort of separation of where my particle is. I should give it, localize it in a wave packet at some particular advanced time v. But well, this isn't localized, right? This is fully delocalized. However, this form makes the integrals much easier. And that's one motivation to use it. It also is known from literature that actually doesn't matter whether you choose this plane wave or localizing things. So since this is convenient, I'll stick to this particular case. Okay. So inserting that particular spherical wave, the amplitude takes this particular form here. So you just get the energy here just pops in. It's some exponential, and there's some normalization factor. I'm not going to track the normalizations here. A couple of reasons for that, but essentially I'm mainly interested in the phase. It's the simplest thing for us to compute, for one thing. Okay, now the amplitude. There's something a bit funny about the amplitude. The funny thing is, it isn't really fully inclusive. I mean, we know that from a couple of points of view. One point of view is, the initial state I shot in was delocalized here. But stuff I shoot in, after the dotted line is obviously going into the black hole. So my observer, in the far future, isn't going to see that stuff popping out. This level of approximation anyway. There's, my detectors are out here. If I wanted to have something that was fully inclusive, I would need to have detectors around the approximate. So there's something that's not fully inclusive about this amplitude, and that's reflected in the log. The log, the integral here is over all v from minus infinity to infinity, but the log goes bad when v goes to 0. So we cut off the integral at 0. So this is the region where we can trust this calculation, and that cut off here is essentially it's just some of the horizon physics that's going into the amplitude. Now this thing, well, it seems to me it's sensible to call it Hawking's amplitude. It was derived in Hawking's original paper. It's the same form. Okay, so now let's switch to pair production. So I had a scattering amplitude. It was 1 to 1. And if you want to actually talk about the production of pairs, well, one thing you can do, if you want to just be very bold, is to take the energy here and cross it from the initial to final state by analytically continuing in E0 to minus E0. So in that crossing, I'll just flip that sign. I change the notation. This is some amplitude A. I'll call this thing B. And then Now you can go ahead and do the integral. The integral is straightforward. There's a gamma function. You pick up some exponential here. This integral here, of course, is also just as straightforward. You just get a different sign for the exponential factor. Oh, for those of you who have managed to stay alert enough to this penultimate talk of the conference, I note that I made a typo here in the slides. That should be an E prime. Sorry. Okay, now counting the number of particles that gets out to infinity just involves, something like a cross section. You take the square of this object B, and with some identities satisfied by the gamma function, you find that this thermal distribution pops out with some overall factor, and you just recover the temperature then. Nice magical identities of the gamma function. Okay, now, well, that crossing was, I waved my hands a little bit. I said that I was being bold. But to get a deeper understanding, it's useful to think about the theory of these Bogoliubov transformations. Now, it's been traditional, of course, to think about this Hawking radiation in terms of Bogoliubov transformations. And all really I want to tell you about these things is that they're also familiar to us in the world of scattering amplitudes. They're basically amplitudes. To, maybe remind you of the theory of Bogoliubov transformations, I'll need to set up a little bit of notation. So in this diagram that I worked very hard on, there's a Hilbert space here, the in-Hilbert space, out Hilbert space. As usual, we have creation, like annihilation operators, matter operators for the in-Hilbert space, A and A dagger. There's some kind of ladder operators for the out Hilbert space, but since there's a relationship, with the S matrix, these guys, the ladder operators in the future, are related to the ladder operators in the past in this way. Right? So B is just S dagger A S. Now, in the situation at hand, it's possible to establish a much more powerful relationship between the A's and the B's. So the way this goes is that, the simplification is that the field equation is a linear, homogeneous, second-order partial differential equation. So we can solve this equation to find the basis of solutions with appropriate boundary conditions. Now, there's two bases I want to build. One basis is in the far past, so past basis, I'll call them P. This basis is defined by having boundary conditions so that in the far past you get just plane wave states. So I can expand my quantum field then in terms of this basis in this way. There's the same integral over P because these states are parameterized by the on-shell data in the far past. Here's the mode functions, these P's, and the appropriate operator to shove there is the annihilation operator in the far past, because as t goes to minus infinity, this thing becomes e to the minus I p dot x. We can do exactly the same thing in the future. There's some other basis functions, the future functions f. They have the property that in the far future, t goes to plus infinity, you get plane waves. So I can therefore expand the quantum field again in terms of these f's. And because the f's satisfy these boundary conditions in the future, the coefficients are the future ladder operators, the D's. But now it's just one quantum field, so those are equal. And because of this, I'm going to be able to establish a linear relationship between the ladder operators. So the way that goes, for example, is to write the P itself, this function, in terms of the basis, the F's. So the P is just some sort of sum over F's and F bars, right? So there's some coefficient A and B. P is some complex function. There'd be no reason why you wouldn't get an F. So, well, if I use this equation in here and then gather the coefficient, gather the coefficient of F. The coefficient of F is B by definition. Well, then you'll find a relationship like this. So the B, which is S dagger AS, is given by an expression. So it's sum over. These are the Bogoliubov coefficients, the A and the B. Okay, now the interesting thing about these is that the Bogoliubov coefficients are generalized amplitudes. Right? So what I mean by these are, well, it's straightforward to see that if I take this expression for S dagger AS, shove it into this formula here, so there's an S dagger AS, Well, there's an A dagger which is creating a particle on the omega. The omega is just the vacuum of the scalar field in this Vaidya background. So, well, this thing will create a particle. I shove in this expression, well, I can get the A there, that will give me something non-zero. In the contraction, the B drops out because the A dagger will kill the omega on the other side. So this Bogoliubov coefficient is an in amplitude. So you create something, you go to the future, you annihilate something, you come back to the past. It's an in sort of. We've heard a lot about in correlators or in on-shell functions in this conference. Well, yeah, I don't know if we have a fantastic name for them. It seems to me that we might as well call them generalized amplitudes. They're on-shell, I could shove some identity in here. Anyway, these are some kind of amplitudes. It's the same for the B. Well, the same story. It's a little bit different. They're essentially crossings of one another. Take this A dagger and shove it over to the other side. That's the B. So indeed, there's some crossing relationship between the A and the B. So that justifies the analytic continuation I was talking about before. Yeah, that analytic continuation is very well. In addition, it is the perturbative expansion of these generalized amplitudes is a Lippmann-Schwinger series, a Born series, exactly as in Julia's talk. So that's why the diagrams I was computing are relevant to this problem. And this Hawking amplitude I was talking about isn't really an amplitude, it's a generalized amplitude. It's an A. Okay, well, now the observable in the future that we care about talking about is just the number of particles, A dagger A, it's in the future, it's an S dagger here. Well, if you use this, this Bogoliubov story, you can rewrite this in terms of those B's, and the square of that, well, this B is essentially that, analytic, that B I cooked up by continuing the A, so this is why you get this is why this is the relevant thing to compute. You really just do need to do that crossing squared. I can see the. Okay, Mr. Chairman. I have no idea how much time I have. 8 minutes, fantastic, I have loads of minutes. Okay, so now we went to higher order, or the next order, to make sure that we weren't making everything up. So the phase here has an expansion. So this is the phase of the wave function of our particle. It has an expansion like this. Here's this eta that's playing the role of h bar. So this expansion, which is in powers of gm, is the analog of the pm expansion in this problem. So this S0 was the thing I computed before. So this is the leading thing in this sort of like radial action / iconal. And if you go ahead and compute the next order, you find it takes this particular form here. So this involves really taking those one loop diagrams seriously and forming a computation. The computation is actually non-trivial. So the interesting thing about it is that I didn't indicate it here, but there's some remainder, some part downstairs here that doesn't exponentiate, which nevertheless its powers of gm in it. So this is the analog of the quantum remainder if you know about iconals, something that needs to be subtracted in order to find the part that does exponentiate. Now, in the iconal story, we need to worry about that quantum remainder at 2 loop orders. But here, you need to worry about it already at the first order. And in fact, it's divergent, so you need to separate that quite carefully in order to extract this part here. Well, with some judicious foresight, you could see that this term here comes from expanding this function here. So the log minus v plus 4gm. This answer here in the bottom line is this follows from Hawking's work. This is the exact, that's exact in this geometric optics approximation. This is the exact phase. So indeed, the fact that this thing came out is a verification of what we. Now the 4gm here is very interesting. So one thing that's interesting, the 4gm is just this gap between the infalling radiation and the part that I guess the generator of the event horizon brought back out to scry. You want to think that way. So so this shift here is explicitly a manifestation of finite size of the horizon. So so we interpret this additional term then as 1 PM order as being a finite size event. Um, so maybe this is a good point to mention something rather fascinating about this whole story, which is that, you know, if we were to redefine this V to be V plus 4gm, so set V prime to V plus 4gm, I would absorb all of these, this is the only source of perturbative corrections here. In terms of this V prime, the tree level is exact, and it's a translation. Now, maybe this is just me, but I see this every time I do some computations in general relativity. The Kerr-Schild metrics are an example of this, where there's some tree level thing, you do translation, now the tree level is exact. This is the same. I don't know. Okay, now my main message here is that we seem to be, maybe we didn't know it, but we were getting tooled up on this problem over the past couple of years. And maybe we can actually do something more interesting. This work, I've just translated somebody else's paper into our language. So there's a number of things that would be genuinely interesting to do and would constitute doing something new. Be nice. One nice thing to do would be to remove the dependence on a classical background, which I put in following Hawking. It's pretty obvious what we want to do, and that is to replace start in flat space quantum field theory with a coherent state of initial radiation in the far past. So that corresponds to that red line. Right? So the red line now is just a bunch of, a coherent state of some other field in the problem that we shoot in. We can arrange that the number of quanta in this coherent state are large, so that it is classically, makes sense classically. Make it narrow, so that it has the properties of this Vaidya solution. And then that when it falls into the origin, these things have to collapse into a black hole. So in terms of quantum field theory, well, the black hole is just some system, and we should sum over it inclusively. So there should be some sort of a form factor which, converts that initial state into the final black hole system. We need to introduce a form factor there. And then with that, the computation is really quite straightforward. You see, it is sufficient to shoot in one particle and then cross it. You don't have to worry about making many particles in the final stage. The many particles in the final state have, those come about in the same way as in our gravitational wave calculations, where we compute a one graviton event, but that really exponentiates into a whole state with many gravitons, because each graviton is emitted independently. So here, all the particles are emitted independently. They exponentiate in a similar way. This is what's called squeezing in quantum optics. It's also enough to consider one graviton exchange, because we know from this work that when you add up many gravitons, it's just going to exponentiate. So that's sort of taken care of. Another interesting thing about this is that the pair production is, it seems quite curious to me. We do, the calculation involves some sort of crossing. So, in terms of the amplitude, you have some particle coming in, it's just bending sort of gradually as it passes through space-time. This is being captured by these diagrams. Now, when you cross them into some diagram like this for pair production, pair production is just going to be, it's going to be as delocalized as the bending of the particle. So you picture here of a pair being gradually put on shell over some long period of time through picking up small, soft amounts of energy over extended period. So that's a sort of an interesting picture of the pair production. This must somehow be related to tunneling, I think. I don't know how, but there's this sort of famous work of Wilczek interpreting Hawking radiations and tunneling processes. Okay, and then some more, random topics. We treated the exponentiation very, we know that we're doing geometric optics, so the exponentiation is more or less built in, but it seems to me that there should be a more detailed story about how that exponentiation works. Again, a little bit like what happens in the iconal stationary phase approximations. Which classical physics emerges from. Radiation reaction is a topic that's been very important in gravitational waves. Here, the physics would be, again, very similar. There's the physics of radiation reaction to pair emission. There's going to be some loop diagrams associated with this, associated with back reaction to the Hawking radiation. A longer-term goal, obviously, would be to understand the page curve, which is would be of major interest to people beyond scattering functions. Okay, that's it.
Thank you for the really nice talk. I would like to understand a bit better your treatment of the V parameter, because at first, again, you say that V over 4gm is some kind of perturbative parameter of your treatment, right at the beginning, which I guess, I mean, it's supposed to be ideally big in the sense that V is supposed to be very close to minus infinity and go towards 4gm, which is exactly the radius at which the black hole forms. So, and in fact, at some point, you integrate from minus infinity to 0 at first, and you get some result that is minus V. And then at the end, with this one loop correction, you get this minus V plus 4gm that seems to correctly tell you that really V should go not from minus infinity to 0, but from minus infinity to minus 4gm. So I would like to understand a bit better what's going on from this point of view, because naively, I would have started directly at 3 level, let's say, from minus infinity to minus 4gm, since what comes after is absorbed by the black hole, but maybe I'm missing something. Thank you.
Well, yeah, there's a lot to say about this, which is, yeah. I mean, the simplest way to think about it is in this form here. So, you know, I'm expanding this phase S in powers of GM. So the phase, well, I mean, we're in a situation where it's a luxury situation. We know what the phase is, so it's this quantity here. So I'm expanding this thing in powers of 4GM. So the leading term is just this log minus V, and then there's going to be all of these corrections that look, you know, that have these GM over V corrections. So at one level, you know, you know, you might think, of course, you know, the structure of the series is very simple, right? You know, just resums, right? You've got a finite ranges of convergence here. It's a luxurious situation. So now, indeed, if you expand in this GM over V, there's going to be this tower of corrections, and you can just go ahead and compute them. And if you want to be you know, very safe, you can just always work in this region where V is large compared to 4GM, and hope, you know, maybe this would be an interesting thing to do. I mean, the series being so simple, maybe you could just go ahead and compute all of the terms in one fell swoop and resum them. That would be great. I mean, we didn't do that, but that would be very interesting. But of course, you know, another thing we know about this, because we have the exact solution, is that this is the right answer. And then given that this is the right answer, I can always translate away the 4GM by choice of the origin V. And in that respect, you know, well, then you might as well neglect these terms. I mean, that's the sense in which this amplitude of Hawking, you know, which I wrote here. So this thing is the exact answer, even though it just comes from the tree calculation, including with the 0, because when you do the translation to get rid of the 4GM, then the location of the start of the horizon just goes to the origin. So okay. This really is the right.
Okay, but so this V ideally is already the V translated by minus 4gm?
Yeah, well, it depends on how. Of course, if you're just, you know, if you're a perturbative person, you don't get to know what, you know, where the V starts at. But so if you want to be, you know, a virtuous perturbative person, you're just going to go ahead and compute your full series, and then hope to resum it. But you know, as is often the case in gravity, the tree approximation gets you further than you would expect.
Thank you.
Any other questions? If not, oh. What other semi-classical observables you would love to compute besides Hawking radiation using this formalism?
No, so we just looked at Hawking radiation.
But what do you think in the future? What can we compute with?
I mean, in fairness, we don't need to go to the future. In the past, people have already computed semi-classical corrections to the potential, the interaction potential between black holes. So, I think this was with Neil's master's thesis. Yeah, good advisor.
Okay, yeah. So let's think.
I have a question. If you scatter just a wave against a Newtonian potential, you still get this IR tail. And I think you're going to get a very similar factor. This is this so-called Sommerfeld factor, right? Can you comment on, like, Should we interpret that in terms of the temperature? It seems that this is a very IR effect that we see also in QED. There it doesn't depend on energy, so you can interpret it as a thermal spectrum, but there's also a similar factor.
Well, yeah, that's actually that's exactly right. Actually, I meant to mention this. So one can, this being QCD meets gravity, one could take the square root of this whole calculation. The Vaidya has a single copy, the amplitudes have a single copy, and indeed you get one power, it's got less energy, drop in energy, so the resulting thing is not thermal. It's true. I mean, I don't have a lot to say. This factor is ubiquitous. It's just in this case, what seems to be interesting about it is the time-like impact parameter that allows this thing to essentially become sort of a radiated process. But yeah, I agree with you that it's very infrared, and I think the physics is surprisingly universal. You don't really know what. I mean, it is the same like conal as in Schwarzschild. It's the same number.
Okay, so let's thank Donal.